Let's move on to section 13.3. This is tests concerning differences between means. As with confidence intervals, when we're considering tests of the difference between two means, we're going to focus on determining whether or not there is a difference or if one mean exceeds the other. So for example, if the two population means are the same, then their difference is 0, since mu equal to mu2 would say that mu1 minus mu2 is 0. Likewise, if one of the means exceeds the other, we expect to show that either mu1 is less than 2 or that mu1 is greater than 2. So that will tell us some information about our alternative hypotheses. And as was shown in chapter 11, making such comparisons requires use of the sampling distribution for x1 bar minus x2 bar in the cases when we're working with independent random samples. In particular, we're going to need the mean for x1 bar minus x2 bar and the standard deviation of x1 bar minus x2 bar in order to compute the test statistic. Let's just take a step back for a minute before we plunge into the details of these types of tests concerning the differences between two means, and just think about the fact that in reality, many practical applications of statistics involve comparisons of two different population means. For example, a researcher might be interested in determining if men perform better than women on a particular test. Similarly, a researcher might be interested in determining if a particular weight loss program is effective. These two examples compare two different means. However, there's a fundamental difference between these examples. In the first example, two samples are independent, say the men and the women, and we should think of independence as meaning that there's no relation between the specific values of the two populations. Given that fact, it hardly seems possible to consider the second example as the comparison between two independent populations. Remember, our second example is interested in determining if a particular weight loss program is effective. The only way that could be possible is if the before weights were recorded from one group of subjects while the after weights were recorded from an entirely different group of subjects, but this wouldn't be particularly useful as a method for determining the effectiveness of a weight loss program. So for the second example, the samples will be considered dependent. In other words, the weight measurements we want to be recorded from the same subjects both before and after the implementation of the weight loss program. As such, when we're looking at the tests concerning the differences between means, we're going to need to determine whether or not we're working with independent samples or dependent samples. And we've already visited the notion of constructing a confidence interval between the difference of means when working with independent samples. So today we'll revisit that in the context of a hypothesis test, and then we'll go one step further and talk about a hypothesis test for dependent samples, and then we'll even use that to help us generalize to a confidence interval for that scenario. The most important thing to remember here is that the procedure for performing hypothesis tests is essentially the same. The only thing that changes from one test to another are the formulas for the test statistic and the distribution that we use when constructing a rejection region. Likewise, if we're using a p-value approach, our methods for computing p-values for one or two-sided tests remain the same, provided that we're selecting the appropriate distribution curve when we're computing a probability. Let's look at the two-sample z procedure for the difference of means. As before, we're going to start by looking at assumptions, and these assumptions will be necessary in order to perform this test. So the first assumption is that we're looking at independent random samples of size m1 and n2 drawn from normal populations with means mu1 and mu2. And in this case, we're assuming that we know the value of the population variances sigma 1 squared and sigma 2 squared. The hypotheses in the associated critical regions will be defined as follows. So for the null hypothesis, we'll say that mu1 minus mu2 is equal to delta, some number, or in the case when delta equals 0, that will be the equivalent of saying that mu1 is equal to mu2. The options for our alternative hypothesis are as follows. mu1 minus mu2 is not equal to delta, that will be our two-tailed test, and the associated rejection region for that will be the set of all z values where the absolute value of z is greater than or equal to z alpha over 2. Or an alternative that would say mu1 minus mu2 is less than delta. That will be our left-tailed test. And the rejection region for that type of test will be the set of all z values where z is less than or equal to negative z alpha. And then the last option would be that mu1 minus mu2 is greater than delta. And in this case, that will be our right-tailed test. And our rejection region will be the set of z values greater than z alpha. As with confidence intervals, given that our samples are independent and drawn from normal populations, we can say something about the distribution of x1 bar minus x2 bar. In particular, the mean of the distribution for x1 bar minus x2 bar is given by mu1 minus mu2. If our null hypothesis then is that mu1 minus mu2 is equal to some delta, then when we're computing our test statistic, we're going to take our sample means, x1 bar minus x2 bar, and subtract their difference, which is given to us by the null hypothesis with delta. Then we'll divide by the standard deviation for the x1 bar minus x2 bar variable, and again that's given to us to be sigma 1 squared over n1 plus sigma 2 squared over n2, and we'll take the square root of that to get our standard deviation. Now it's worth remembering that this procedure should also apply to large samples so long as n1 and n2 are both greater than or equal to 30. In such a case, we'll apply the central limit theorem to approximate the sampling distribution of x1 bar minus x2 bar with a normal distribution, even if our original populations are not normal. Furthermore, if sigma 1 squared and sigma 2 squared are unknown, then we'll use the sample variances s1 squared and s2 squared as estimates for the sigma 1 squared and the sigma 2 squared in the test statistic formula above. What happens in the case where we are drawing independent random samples from normal populations, but either one or both of the sample sizes are less than 30 and our variances are unknown? Then we're going to proceed similarly to the way we did with confidence intervals. In particular, we're going to look at a two-sample pooled t-test for the difference of means. So the highlighting features of this are that we probably are likely to have either one or more of our independent random samples being small, and our variances are unknown, but we'll be assuming that the variances are equal. So our assumption is that sigma 1 squared is equal to sigma 2 squared. Our hypotheses and associated critical regions will be defined as follows. As before, our null hypothesis, in the case that where we're assuming that delta is equal to 0, would say that mu1 minus mu2 is equal to 0, or that mu1 is equal to mu2. In the event that delta is not 0, then we'll just say that our null hypothesis says that mu1 minus mu2 is equal to delta. This is in contrast to our alternative hypotheses, which would say, for the two-tailed hypothesis, that would say that mu1 minus mu2 is not equal to delta, or 0 if our delta is 0, and our rejection region then would be the set of t values where the absolute value of t is greater than or equal to a t alpha over 2 score, which is computed using n1 plus n2 minus 2 degrees of freedom. The second option for an alternative hypothesis would be that mu1 minus mu2 is less than delta. This is our left-tailed option, and in this case our rejection region is going to be the set of t values where t is less than some t negative t alpha score, which is computed with n1 plus n2 minus 2 degrees of freedom. Our final option for an alternative hypothesis would be that mu1 minus mu2 is greater than delta. This is our right-tailed option. And the associated rejection region will be the set of t values where t is greater than or equal to t alpha, and that's computed with n1 plus n2 minus 2 degrees of freedom. The test statistic will be given by t equal to the difference in the sample means minus the hypothesized difference in the population means divided by SP, which is the estimate of pooled standard deviation, multiplied by the square root of 1 over n1 plus 1 over n2. Now remember, this is a t-score that's going to be computed with degrees of freedom equal to n1 plus n2 minus 2, and we'll generate the estimate of pooled variance by computing SP squared equal to 1 less than the sample size for the first sample times the variance of the first sample, plus 1 less than the sample size of the second sample times the variance of the second sample, divided by the number of degrees of freedom. This computes our estimate of pooled variance, which we then take the square root of to use in the formula for our test statistic. Let's look at an example. In the summer of 1988, Yellowstone National Park suffered the devastating effects of several major forest fires that destroyed large tracts of old timber near many famous streams. Many fishermen have been concerned about the long-term effects of the fires on the streams. However, some biologists have argued that the growth of new meadows would produce more of the insects on which the fish would feed. In other words, the biologists are suggesting that there's a possibility that improved fishing could be a long-term effect of these 1988 fires. And rangers have collected data detailing the number of fish caught by fishermen on a daily basis. And the park's publication, Yellowstone Today, has indicated that the biologist's claim has been correct and that fishermen have been satisfied by the increase in their daily catch. So suppose we've visited a Yellowstone ranger station and we've gathered some actual data from fishing reports. So consider the data provided below from independent random samples. that give information on the number of fish caught per day. Before the fires, we've got a sample of 167 days, and the sample mean for the number of fish caught per day, 5.2, and the sample standard deviation is 1.9. Then consider an independent random sample of 125 days selected after the fire, where the mean catch was 6.8 fish per day, and the standard deviation is 2.3. So our job is to determine whether or not there's evidence to suggest that the mean number of fish caught after the fires exceeds the mean number of fish caught before the fires. And we'll assume that we're working with equal variances for these two populations, and we'll let the significance level of our test alpha be 0.025. So first, to just make sure we recognize which test we're doing and that it's appropriate, we're going to assume that we have independent random samples. In this case, we don't know if our samples are drawn from a normal population or not, so we can just recognize that both sample sizes are greater than or equal to 30, so we have large samples, and we're assuming that we have equal variances. That tells us that we're going to be working with a pooled samples t-test. So to get started, we'll calculate the estimate of the pooled standard deviation by making use of the formula that we had on a slide a couple slides ago. So we'll take 1 less than the sample size of the first population, multiply it by the sample variance for the first population, add to that 1 less than the sample size from the second population multiplied by the sample variance for the second population, divide by the number of degrees of freedom, and then take the square root, and we'll get our estimate of pooled standard deviation to be 2.08. Then we'll think about what our hypotheses are. Our null hypothesis is going to say that the mean number of fish caught before the fire is equal to the mean number of fish caught after the fire. So we're saying we don't think there's any difference between those means. The alternative hypothesis would say that the mean number of fish caught before the fire is less than the mean number of fish caught after the fire. This is the claim of the biologists. So this will give us the equivalent of saying that the means for before the fire minus the mean for after the fire is less than 0, so that tells us we're working with a left-tailed test. Step 2 says let's determine our critical region for this left-tailed test. So alpha is given to be 0.025. Our degrees of freedom would be the 167 plus the 125 minus 2. That gives us 290 degrees of freedom. So we're looking for a t-score with an area of 0.025 in the tail with 290 degrees of freedom. So if we look in our t-table in the book, it doesn't give us this value precisely. It jumps between something like 200 to 300 degrees of freedom. If we go and we look it up on a computer or using a calculator, would tell us that the critical value for t of interest is 1.968. So our rejection region for this left-tailed test will be the set of t values where t is less than or equal to negative 1.968. Now we'll compute our test statistic. Our t-score, we look at the difference of the two sample means, subtract off the difference that's hypothesized in the null hypothesis, divide by the product of the estimate of pooled standard deviation and the square root of the sum of the reciprocals of the sample sizes. This gives us a test statistic of negative 6.5. Now this test statistic of negative 6.5 lies in the rejection region because it's less than negative 1.968. So that tells us that there's evidence to suggest that the mean number of fish caught after the fires exceeds the mean number of fish caught before the fires. And given that our test statistic of negative 0.65 is so much less than the negative 1.968, then that suggests that perhaps there's even strong evidence to suggest that more fish are being caught after the fire than before the fire.